Mark?
We are recording now. We just went live. Okay,
Oh,
we're
okay.
live on YouTube. Cheers, everyone, from Hawthorne, New Jersey. We got Drew, sunny Florida.
Oh, yeah, Drew in sunny Florida.
And Warren, you're out in California, right?
Yep, I'm out here. I'm working with Jim Woodward on the Mach effect experiment, and also doing some theory work in general relativity and physics.
So actually, Curtis, I wanted to ask you about that. I got some emails from Jim Woodward today over the past few days saying that there was some technical problems and sending me a device. We wanted to do the high-speed camera footage. So what's the status on that?
Yeah, I think Jim has been working. I mean, we had some issues where there was some wiring issues. Some things looked like they were broken, but luckily they weren't. So we're working through that. And Jim is still kind of trying to understand the new devices we have. So I don't know if you recall this, but we basically weren't able to get the old material that we used to get. And so we have new stacks that were made by another manufacturer that's active. And so he's active. He's basically trying to characterize these new devices and kind of see, he's doing runs like every day. Like today, he did a bunch of runs as well, and got them processed with Michelle. And so I think he wants to make sure to send you something that he thinks has a good shot of working and not being stick slip only. So the stick step motion still happens. It's clear when you look at the analysis, where one thing goes one way, the other one goes the opposite. That's clear stick slip, right? So basically, I think he's very conservative in terms of characterizing what he sends out. So that's why he's taking this
out. System overall. But
can you repeat the question? It kind of broke up.
Yeah, I couldn't hear it either.
How complex is the your setup? Like how much is involved in getting the device to work? The Woodward effect.
Well, once it's, I think that the matter is getting the circuit correct that you're hooking the device up to, meaning that you need to have, basically, we need to send you the inductor that couples with it. And from there, as long as you can power it. So right now we're using an amplifier, this carbon amplifier, and that's run by a function generator. So really somebody with some lab experience, it shouldn't be too hard. But the actual device itself, whether, a lot of times if it's not running, Jim will take it apart, rework it, retorque things down. That part is intricate work. So that's what kind of takes a while. So actually, once you get a device that we know is working, it shouldn't be too hard for you to actually run it in your lab.
Curtis, you got any kind of I've been watching your stuff for, I don't know, over a year now. And I still really don't understand what this thing does. It's a little oscillator, and could you just give us 5 minutes on it? I don't want to,
Sure.
I don't want to break any patents or anything. I don't truly understand the dream.
No, it's understood. So basically what it boils down to is things, you can think of them this way. Things weigh more when they have more energy inside of them, right? We know that energy and mass are sort of have equivalent reactions to being moved. And so what Jim has found is a way to take advantage of basically he's using special relativity, I would say, and a little bit of general relativity, like a linear approximation. And what happens is that when you have more energy in the system and it's pushing against the basically as the piezo stack is pushing out on the two masses, if the masses are uneven, it's going to get a different reaction from each mass, right? And if it's pushing out and it has a different weight, then when it pulls back in or gets the reaction happening, you can have a preferential movement of one side or other, meaning that when you're getting the reaction back, you'll be pushed in one direction versus another. So, and the reason that happens is that you're removing energy. You're putting energy in, and you're removing energy, and that addition and removal of energy has to coincide with the mechanical vibrations in such a way that you get this preferential movement. And if you don't get that resonance just right, and everything's not lined up, you're not going to see anything. So it's kind of like threading like 7 needles at once or something. It's a very tricky thing to do. Now, the issue with it in a real experiment or real application is that because that vibration is, is so strong, and you need to have that vibration not be constrained. It's not very easy to actually practically build a device that does this. So that's one of the problems. So one of the things with the ears is that we have these bearings, and what we used to have, and I fought tooth and nail to get this out. They used to have these metal ball bearings on metal rods. And you can imagine you're vibrating this thing at like 30 kilohertz. Those things are scorching all the time. So the device would actually work great, like a few runs, and you would see it. You would see it move, and then all of a sudden it was just like a bunch of noise because the ball bearings would scorch the rods, and they would get stuck and unstuck, and all this crazy stuff would happen. And so basically the devices weren't repeatable. So now we're using composite bearings. And that being said, even with composite bearings, they're not, they have a certain friction coefficient. So you're still getting like stick slip type motion where the actual supports are the issue here, where the supports could be like sticking on one side and then slipping and then sticking and slipping and sticking and kind of causing a motion. And so we're trying to differentiate the stick slip from the actual motion that we're putting in. And then things are further compounded by the fact that it's on a torsion balance, which is, I consider, a non-linear equilibrium. It's like being on top of a hill, and you're balanced right there, and you have a little bit of a sine, x squared type motion, but it's, if you go too far, all of a sudden it can look like there's a force when there's not. It's just unbalanced.
An unstable tip of the mountain where.
Right. So the regime is really tiny, where it's like a stable equilibrium, and you go out and you're like all of a sudden unstable. So that's why we're looking at like doing other experiments and other setups, and it's very slow going because any change you make affects that resonance. And so there's no easy answer with it, that unfortunately. So that's why it's
I'm still trying to figure this out. So basically you have a mass, and you have a piezo.
Let me try to explain it, and Curtis, you tell me if this is wrong or right.
Okay.
So mass equals energy, energy equals mass. What they're doing is they're vibrating basically a capacitor and or an inductor. They're converting energy from one form to another, and in the same time vibrating it back and forth. So here the energy is potential, and then it becomes physical, and they're bouncing it back and forth in resonance with the vibration. So you're able to vibrate and move in one direction because the mass is there, and then it's not. It's there, and then it's not. It's there, and then it's not. So you have an electrical circuit that is in tune with a physical vibration that makes energy become matter and then back and forth. Like a capacitor filling up with charge would weigh more than a capacitor that's empty.
Okay.
Yeah,
that's a very interesting statement. And I'm not saying it's not true, but is it true? I mean, has anyone actually run
Yes.
this test where they've taken a symmetrical capacitor and charged it up and seen a mass increase?
Well, a capacitor
Or a
is
weight increase?
the thing is, for the effect that Jim is talking about, the capacitor doesn't do it. But in terms of like energy mass equivalent, that's like a known thing. Now, all that being said, there's a couple things I need to say about that. Number one is that we want to do the experiment where the device and the power source are on the same, basically the same kind of rig where they're both moving, right? So there's a whole set of experiments that need to happen to really like convince myself that, okay, this is real. Because if you're putting energy in, energy mass equivalent, you're taking it out. Well, what's to say that's going to be useful? Maybe that device does move, but what if the source cancels that out if it's all together in a ship, right? So so there's other steps to go before we say, okay, yeah, we can use this in a ship, in space, and whatever, right? So right now the power source is external to the device. So that's where we're at now. The other analogy, I was going to give you another analogy, which kind of works really well, is that like if you think of a kayak on the water, right? And you pick up some buckets and you're like, moving yourself back and forth, and you pour the water out. When you're moving one way, right, you have more momentum that way. You pour the water out and go back. You pick up the water, you go forward, you pour the water out, go back. And that way, you're kind of taking momentum from the water, right? And you're pushing yourself along. That's the analogy for this. It's basically because when you're doing this motion, you're basically kind of taking the reaction effect of the rest of the universe. That inertia, when you push on something, you have to push, right? There's a pushback, right? That inertia is what the energy you're kind of using for that net motion. It's kind of like a little trick, just like with the buckets. There's also analogy in electromagnetism for electrons called the radiation self reaction of electrons. So there's actually analogous theories in E&M that do the same kind of thing, where you can have self energy, right? So those, and that's a well-known accepted thing that's measured. But here we're doing it with inertial mass. So a lot of it depends on how the atoms are moving, right? How the nuclei are moving, because the nuclei are the ones that have most of the mass. So we're putting electrons in there. And the thing that's interesting about the equation Jim derived is that force, or that change in mass, the delta M, is actually proportional to the change in power over time. So the faster we take out the power and faster we put it in while we're doing this vibration, the more we get that effect of a push.
Interesting. And what level of force have you seen so far?
Well, tentatively, for short times, it could be in the newtons. But again, that's so much that it's makes we need to confirm that there's not stick slip or some kind of unbalanced thing. So we need to do other experimental configurations to confirm that it's something else. Now, I have been looking at a magnetic slide with some. The thing about magnetic slides is that they're kind of unstable, right? So I'm thinking of putting some roller bearings and just having something that the roller bearings are there just for stabilization, and because the problem is that we need to do this in a vacuum, and if you use an air bearing, you're not in a vacuum. So one of the ways we're trying to get around that is we're going to use an air bearing with the device in a little vacuum capsule, right? But that's kind of difficult because you have to vacuum it out. You have a valve, and the thing will it'll fill back up with the things will off gas and the vacuum will go away eventually. So there's experimental difficulties that we're trying to overcome as well.
What if you put your device in outer space? Would it work?
Well, that's the big question, right? That's what we want to see. We want to know, would it work with zero gravity? There's the idea, like I had the idea of like going on the vomit comment, but like, things are so dynamic there, that'd be a tough experiment to do, even if you have like, what do you have, like 30 seconds? I don't know. But
well, you've always got you got about 4 minutes.
4 minutes.
Blue Origin has their little New Shepard, which gives you about 4 minutes of zero grav.
New Glenn, you owe me a beer, Drew.
What now?
You owe me a loaf of sourdough. The new Glenn made it.
Yeah, actually, I was very impressed. Really, I was. It woke me up and everything because I was sleeping at the time that thing went. But to get back to the test, they have a box. Because I looked into the prices of the New Shepard, and the box is roughly, I'd say about 18 by 18 by about maybe 8 inches. And anything you want to put in that box, of course, gets about 4 minutes of zero grav. So they're a little pricey. I think it's around $100,000 or so for the trip. But that's that's certainly more time than you're going to get in one contiguous span than from the parabolic arcs, and
the trick is having the vacuum. So you'd have to have the vacuum.
Yeah, that is tricky.
Right? Yeah, that's the tricky part.
But in that case, the whole box could be in vacuum.
Yep. Yeah, and I think that in terms of the vacuum itself, the reason we have the vacuum is that the device interacts with the air and actually becomes an air pump, right? It pushes the air one way. There's vorticity happening, and actually we did a console simulation years ago. Hal had that done, and we found out that the thing will like produce a Newton. That little device that we have can produce up to a Newton of force in the air. So that's why a lot of times when we get all these replications that don't see anything, we get really suspicious because they should see something, right? They should see stick slip, and they should see the air moving it, especially if the experiments were done in there.
I'll give you a little example of why that may or may not be true. When we started out with our simulations, we were supposed to be seeing 2 or 3 Newtons. Our electrostatic fields, our areas. We ran the numbers and ComSol, or I don't know, all kinds of different simulations. But anyhow, the short and long of it, we were supposed to be seeing Newtons of force, and we could not get anywhere near that. We're in like the 100 millinewton, or I'm sorry, we're in like the 100 micronewton range or the 1 millinewton range, and we're like, what is going on? How can we possibly be this wrong? The answer turned out to be alpha. It turned out that we were missing a piece of the fundamental formula, and as soon as we slipped alpha in, which I'm not entirely positive what it is, but Dr. Charles is completely conversant in this. As soon as we slipped in that alpha thing, and it instantaneously solved the scale problem, and then it said, hey, you're supposed to be making a millinewton. Boom, we were making a millinewton. And since then, we've never made that same mistake. We've made lots of other mistakes, but we've never made that same mistake again. Is it possible that somehow, if you're seeing micronewtons of force regularly and your equations are saying newtons, is it possible that maybe you're missing some giant fundamental thing that's eating your lunch?
Well, that simulation was done in an atmosphere. So it simulated the atmosphere around the device, and it was a simplified simulation. So basically the thing hanging there in space. Our experiment at the time was hanging from a pendulum. And so we were seeing a definite force of several tens, hundreds of millinewtons. So we were getting close to that. I mean, I understand that that simulation was ideal because like it hits a frequency exactly, and we're not doing that. We were sweeping. So we were sweeping and we were like around the resonance. But the simulation is able to show you at resonance what you're getting if you're pushing for a while. So we were seeing it experimentally as well in the air. And when we put baffles around it so that the air couldn't move anything, of course, the force went away. So we basically confirmed that it is an air pump that can actually push air. So that was confirmed experimentally. And like I said, the simulation, it's ideal resonance. You can't like with our devices, you can't practically hit resonance because it's always moving with temperature. It like drifts right away. And we don't have any sophisticated tracking electronics that would follow it. So, yeah, it's kind of what we expected, where we'd have a fraction of that, and that was confirmed. If that makes sense.
Yeah. Yeah, we also had a big problem with resonance. We were using, when early on, we were only making 20, 30 micronewtons of force. We would welcome resonance. We'd sit there and hit the circuit. I don't know, 2, 3, 4, 500 hertz, and we would find, or was it pi? I can't remember. Maybe it was pi. Maybe we used to hit it at pi, which we thought was very curious. But when we were hitting it, all of a sudden the forces would just blossom, and we'd be making 10, 20 times the static force in its resonance form. And it was enough to where we could get above the signal to noise ratio and actually see that we were doing something of any actual interest. So I don't understand. I mean, you operate in resonance. That's the sweet point of your system. Is when you hit mechanical resonance.
Yeah, well, it's a combination resonance.
I mean, that's like
the thing is
like the edge of it's like when the dynamite blows up. How do you get any measurements?
The thing is, so you have a piezo stack vibrating, right? And against it are is the aluminum and the brass. So the entire thing has a mechanical resonance where if you're at that resonance, the material is, you get waves of, you call it sound, right? Pressure waves that go and bounce back. And when it bounces back, if it's not at the right, like a fourth order or a positive order resonance where it's hitting back, and if the piezo stack's pushing when that hits back, you're kind of canceling things out, right? It needs to be in line with what's happening with the vibration. So those higher order resonances, we can see that when the second order resonance goes above the first order, like all the positive resonance go higher, and the first and third order go lower. We can see that that's when the effect actually happens. That we're getting things are lining up in the right way to produce the effect. So that's kind of a necessity for this thing to happen, because you know how it is. These materials, they're not rigid, right? They're like vibrating all over the place like crazy. So we need to be in line with those vibrations, and that's part of the issue. Is that with those vibrations, it makes things where other things can happen, like the stick slip, right? So the supports we have are like I think of them as almost tuning forks sticking out, and they're clearly going to be vibrating, right, at those frequencies. And when you're vibrating like this and you're on a rod, you could easily be walking yourself back and forth. So that's what we're trying to like figure out a way, supports that won't do that. So I was looking at other bearing solutions, but the issue is that we have such a small device that those bearing solutions are on the order of the size of the device itself. So it's kind of impractical to like add that to the experiment at this point without major revisions.
Why do you need the bearings in the first place? Can't you get rid of them and just suspend the entire device off of like 4 strings or something like that?
Well, that's the thing. Where do you put the strings, and how tight do you put them? See, if we there is an idea to put some strings, and we've done that. But the thing about it is that if you, depending on where you put the strings, you can dampen the resonance, right? So you need to put the supports in a place where you're not hindering the mechanism from appearing. So that's kind of the issue. Like when early on I would ask all these questions, why don't we do this, that, or the other, and basically a lot of the development of where we are now came from understanding basically that you need to get resonance, you need to get certain resonances for the effect to appear.
Mm-hmm. It sounds like an experiment that really should be done in outer space.
Yeah, well,
it's an expensive
statement. You know, that's yeah, that's the reason why I'm looking at like a trying to do a magnetic rail with some bearings for kind of support or just like alignment, because I think that once we're able to show that we're able to get like a linear in a stable equilibrium, that we're able to get a linear push, because something like that, if you have stick slip, it won't go anywhere. It'll like go back and forth, but it won't actually move, right? So it's a good experiment that way. And then the next thing I want to do, if we can confirm that, is actually put it on something like something in the water, where it's floating.
What if instead of putting something in the water, you put it on a bed of ball bearings or a bed of ping pong balls?
A lot of sticks.
Yeah. The thing about, okay, so it would have to be isolated in a way where the vibration doesn't transfer, right? In any case. So as long as we're producing enough force, we should be able to overcome, with a small vessel. That's what we're thinking about now. But anything where we can have a vacuum, right? That's going to have some weight to it. But ideally, we would be able to move the whole entire device. So a vacuum you could do with, aluminum. There's lighter things. There's some.
Curtis, I got to ask some basic stuff here. All right, let's say this is just a little stack that you could get into, you could get it into resonance, right?
Right.
Okay, and you put your piezoelectric thing on one side, and I guess you put another one on the other side. Let's say this is your whole device. Okay, it's not on a rail; it's just kind of suspended on a tuning fork thing.
Okay.
If you put the piezo thing on, I don't know, one or both sides, I don't know how you do that, and you hit the button, you could get that thing into resonance, right?
Yeah.
Okay, and then you're saying that at some point you would put a capacitor of some sort on here somewhere, right?
Well, the piezo stack does have capacitance. So the piezo stack, it's a stack of, right now it's about 8 piezoelectric discs, and we have positive and negative, and each stack we basically put voltage in, we put electrical power in.
So while this thing is piezo vibrating, you could turn on some kind of frequency and charge those plates up, and it wouldn't mess with the piezoelectric effect. Does it mess with that, or?
Yeah. What happens is, okay, so we have the piezo disc, and we have 2 electrodes on either side that are sandwiched in there, and we have a stack of 8. And what happens is in the discs inside is that as we put a charge, it'll expand as we charge it up. So it has a bunch of, more energy as we're charging it up. It expands, and we take it out, it contracts, and that's what it does. So you're getting in there, you're getting electrical, power, right, from the voltage that we're throwing in, the electrons, and then we're taking them out. You're losing that you're doing that.
You put the power in, and what? It physically makes everything expand?
Yeah, it physically expands. So, yes.
And does that affect your I'm not sure how a piezo thing works. So I guess you put in.
Okay, so the way a piezo stack, what a piezoelectric is a crystalline structure. So with beer bottles, Imagine it's kind of like this. This is half of half of the crystalline structure, and when you squeeze it, now I'm squeezing it, you create a voltage potential. So you know those little lighters that you kind of click down and they make a spark and it lights it up?
Yeah.
What they're actually doing is you're hitting the piezo, the crystal, and it goes like this, and that shifts electrons around and creates a high voltage on the surface of the crystal, and then you get a big spark. The same thing can happen the other way around. You can apply voltage to a piezo crystal and it physically changes in size. And you could also talk to a crystal, and that will convert your voice, your vibrations into energy. There's headphones that use it. There's speakers that use it. It works better for microphones than it does for speakers, but that's the piezoelectric effect.
And so this connection between the mechanical and the electrical effects is very critical here, because we're driving the circuit. But as was pointing out by Mark, and what you're maybe thinking about, is that when you expand and the thing is crunched down, so it's sandwiched between these two metal, a brass and an aluminum plate, and as that energy of the brass comes back and pushes on that, when the thing comes down, you get electrical energy coming back out. So that's why we have that we have a solenoid that's tuned to a certain frequency. We actually characterize the devices, and we wrap a solenoid to tune to around 30 kilohertz for these particular devices we're building. And what that does is that allows that energy to come out, and that's why those higher order resonances are important, because we need the energy that comes out and gets to the inductor and comes back in to be about the same as when we're pumping it in, right? So we don't want to be canceling out the energy we're putting in. We got to be, adding to it. So that's why those positive higher order resonances are important, because as you shrink down, you get electrical power coming out. It's producing power as well. So it's not just that we're taking away; it's getting pushed out by the piezo stack when it contracts.
Are you worried about the fact that you're feeding in, I guess, high voltage? I'm not sure what these piezo stacks operate at, but that you're feeding in, and every time you change the voltage in a wire, you literally cause the wire to do whatever wires do. They stretch, they bend. You put high voltage through a wire, you can actually watch the wire change shape in response to the voltage.
This is about 100. Yeah, this is about 120 volts at the most, and there's not maybe an amp. It's not a application where we think that's happening. Also, the wires coming up to the device are very small. I forgot what gauge, but they're tiny. So it wouldn't it would be very hard for that tiny wire to be doing what we're seeing. It's more likely to be the stick slip and the unbalanced equilibrium of the torsion pendulum. So, but yeah, stick slip is definitely something. I know Mark pointed out the higher speed cameras. Like I have one that can do 500, or actually can do like maybe 700 FPS, but that's not high enough. You need something that's on the order of the frequency you're putting in, because as the things are vibrating, you need to be able to see it move and see what happens. If they're like moving like this, it's stick slip. If they're just vibrating,
you want a multiple of the frequency. So if it's 30 kilohertz, you're running it out. You want 100, 150.
Yep.
And my camera can do that. It can do 150. So the real question for me is, should we be coming to you, or would it make more sense for you to come to us? Because I could bring the camera. I can't bring the lighting. The lighting is entire, like probably 2 suitcases worth.
Yeah, send me some information on the lighting, and I'll see if there's something we can come up with locally, and then we can talk about it and figure out which way is the best way to go.
I mean, for me, it's obviously better if you came to me.
Yeah, and I think Jim's working towards getting things characterized so he could send you a test article. I don't see why that would be a problem, because it's something that Michelle is able to do as well. She's able to run these devices, and so there's people, there's me, there's Michelle. Hal's retired, so we can't bother Hal, but there's other members of the team like Paul and David. Dave can help as well. So yeah, I really think we should send it to you. That's what I think we should be doing. And if you have ideas about supports, we should talk to Jim about that, because I think that maybe if you can find out what Michelle's doing, we can get a call with her as well. That would probably be a good idea, because Michelle was trying to do like a spiderweb type design, and that is it has some dampening effects, but at the same time, there's not going to be any stick slip when you're using. I mean, it's just not possible, right? With those with nylon wires or whatever she's using. So she has been able to see a movement, but again, she's running it in air with baffles. So the thing about that is that sure, the baffles will take out care of most of the effect, but there might be higher order things with the air, like especially when you're doing those kind of frequencies. You could have in the air, you could have something that penetrates a barrier from the vibration, and has like nodes, and it'll move to a preferential node, right? So until we get the thing in a vacuum and see it move linearly, we're still kind of it's looking like it's there, but I can't say for sure yet.
Yeah, I hear you about the nodes. I was actually on YouTube yesterday, and I saw a video. A guy hooked up a garden hose to a speaker, so that the speaker would vibrate the garden hose up and down. The garden hose was providing a laminar flow, and at certain frequencies, nodes were created that were just standing in space of the water. And I was thinking to myself, that's exactly what we need to do with electricity in order to create a warp field, a field that like a way to tug on objects at a distance using RF.
Yeah. Well, the big trick is going to be understanding inertia in matter. Like right now, the physics community, I see all the nonsense going on. They're just confused about everything. It's really disheartening. So, I don't know. I mean, there has been some good experiments showing kind of like the limits of quantum mechanics, and so there's some people starting to open their eyes about how much we really do know. But I see physics is kind of in a world of hurt right now in terms of like doing anything real. And so that makes it tougher for us, right? Because we're trying to, I'm trying to do physics, and that's why I'm interested in Jim's thing. But, you guys are trying to actually make something move. To me, that'd be cool, but I'm more interested in the physics, because what that means is that if we do something like this, that means that there's something fundamental everyone's missed, right? So that kind of can start opening people up to starting to think like they should be. And I doubt AI is going to save us. I mean, it may if someone guides it. And I have been using some AI tools lately, because I tested it when before GPT, I was testing AI to do certain things, and it can do some cool things. I don't know if you heard about this, but there was a team, they developed an AI called AI Feynman. And what they did, somebody did, is took that AI and they put in the same data that Kepler had when he figured out Kepler's law, right? The experimental data of like the motion of the planets. He put those tables in, and it took, Kepler took him years to figure out his laws. It took a Feynman AI about 4 hours, I think it was. So there is some promising things there that might give us some insight. But yeah, I think we're I think the experimental side of it is going to be important, and testing these different ideas of what really is in the vacuum, what the vacuum is made out of, how you can interact with it. All that stuff is important. And I'm really curious about Drew's stuff. Have you ever built the Borg cube, or what you've done yet?
No Borg cubes. But yeah, we've had a lot of success over the last couple of weeks. So I don't know. Do you want to chat about that, or?
Yeah, sure. Let's go to that.
Okay. The last couple of weeks, I've been focusing on. I've got some potential customers, and they want to see some very specific things. And one of them is stacking. They want to see, they've seen a single plate thruster by itself in the middle of electrically isolated box inside vacuum, and you turn it on, and the thing, makes a millinewton or two of thrust, and it's very impressive. You turn it off, and discharges, and it goes back to zero, and you turn it on, and it goes right back up and makes all the thrust, and you can disconnect the power, and it works fine. It can actually, as long as it stays charged, you can actually disconnect the wires, and as long as the charge has nowhere to go, then the thrust stays on. I've run it for hours on end, and nothing really happens. It takes weeks for the charge to dissipate. But these particular potential customers, they want to see that I can stack these things, because one big one means I'd need something the size of a solar sail if it's just a single layer. And there's nothing wrong with having something the size of a football stadium as your propulsion system, but the logistics of building something like that is ridiculous. So all the last couple of months have been, what's it going to take to have a thruster, and then have another thruster, and then whatever, have another thruster, so that they're all kind of reasonably close to each other, but electrically isolated, so that they don't hurt each other or kill each other. And because these things are electrostatic fields, they love to kill each other. They just love to attack each other and just do all kinds of mischief. So of late, I have taken to, I don't think it's any secret that I operate inside of an ITO box, which is basically 5 mils of PET plastic with, I don't know, a couple of thousand atoms thick of indium tin oxide on the PET to make it into a conductive plastic, basically. A couple of hundred ohms per linear inch, or something a little less than, maybe 100 ohms per linear inch of conductivity. So I operate my entire electrostatic propulsion system inside of basically a Faraday shield, so that the whole assembly, it's just a whole bunch of these stack things, they're all inside of an ITO box. Well, since we measure all the forces from the outside of the box by connecting up to the physical skeleton that everything is built off of, we're not lying to ourselves. So if there's any forces going on, the box is the end of that's it. Whatever else is happening, the box is going to eat the fields that are trying to escape the box, because it's all metal on the inside, and that's all grounded to the chassis ground of the vacuum chamber. So there's no Coulomb effect. So that worked fine, and I figured that's all anybody would ever want to see. But I have a potential customer that wants to see individual. He wants to see that everything, that we can stack up these things and that they're completely isolated from each other. So I went to building what I call pouches. So now I have little ITO pouches, which are the same size as the big box, and I put a plate set inside of the little pouch, So basically now it has, metal walls right outside of the frame. And then I've stacked a bunch of these pouches up inside the big ITO box, and I've just been playing around with sizes and scales and thicknesses, and just to see, how you move these plates a little bit further apart, move them a little closer to each other, bring the pouches to where they're all the way down to direct contact. And it's been very successful. I started out at about 3 inches apart, and as of a couple of nights ago, I had them all the way down to zero contact. So I had, 3 or 4 of these things stacked up together, and they were all in contact with each other, and it made the same amount of thrust as it did at other times. The thrust is significantly lower than a single plate, but you could have 1,000 of these stacked up plates. So you win by attrition. Instead of having one big plate, let's say it's 100 square inches, making, 10 millinewtons of thrust, you could have 100 small plates that make, 120 millinewtons of thrust, just as an example. So you would, or I'm sorry, 20 millinewtons of thrust. So the goal is to get these things to where they can just stack right on top of each other. I mean, that's the ideal condition. Would just be to have layer after layer after layer after layer of these things, and one big ITO box around the outside, and basically just stack these things up, and then you just make the surface area larger. So that's been the basic thrust over the last couple of months, is how to electrically isolate these things so that they don't kill each other. And can I stack them closer and closer and closer, that right up to the 0 point, which is stacked right on top of each other. So that's always a fun thing. And that's pretty much been the driving focus, that and bring the big vacuum chamber online. So that's the goal, is now that I have a stack set. In fact, today I'm actually making up brand new thrusters, because they tend to degrade in performance when the static charge builds up. Actually, it's not a degradation of performance so much as I can only observe the force by setting the force meter to 0 at the start of the test. So at the beginning of the test, take a brand new plate set, stick it in the machine, stick it in the vacuum chamber, hook up the force meter, and turn the thing on. Well, it'll charge up to, say, 600 micronewtons of thrust. And then when I turn off the system, that 600 micronewtons might only drop down to, say, 300. Well, the next time I turn the system on, if I don't record that I'm starting at that 300, the machine just goes to 0. So it says, okay, now let's go, and then it makes 300 more, and then it drops down, but it never drops back down to 0. It might drop down to 100. So what I end up doing is I end up packing up more and more and more, what do they call?
Static thrust.
It's basically it's trapped charge, basically what it is. It's trying to think of all the buzzwords. It's not free charge.
Static thrust.
It's really not static. It's Charlie's got a special term for it. Bound charge. That's what it is. It's charge that has leaked into the polymer, and once the charge gets in the polymer, it really likes to stay in there, and it likes to make thrust. Well, the only way you know that you're making thrust is to set the force meter at 0 at the start of the test, switch it on, and watch the thing go up and stay on, and then you turn it off and the thing comes back down. Unfortunately, if you start here and you're making, you start making thrust, then you turn it off and it comes back down. If it doesn't go all the way back down to 0, you've just packed up some amount of bound charge in the system, which is very cool. It's totally understand. We understand what it is. We can explain what it is. We can actually tell you how much it's going to happen. and it's very predictable. It's very consistent. But the problem we run into is, we can pack up 2, 3, 4, 5, 6, 8, 10 millinewtons of bound charge. I ran this test, I don't know, it's probably been, right at about a year ago. Yeah, maybe not that long. But anyhow, I ran a test a couple of months ago, and yeah, Curtis?
Question. This bound charge, when it's bound up and you're saying that the bound charges stay, how long do they stay? Are they there always?
They stay until they're not there no more. So if it's under vacuum, so if I leave let's say I pack up 10 millinewtons of, and actually I have a graph somewhere of one of these tests. Let's say I packed up 10 millinewtons of bound charge, and then I literally disconnect the wires so that the device is just hanging out in a vacuum chamber. It doesn't have any. There's nowhere for the charge to go.
Right.
It could worm its way through the polymers, and eventually would cancel with the mirror charge on the other side. But that would take forever, literally, because these polymers are pretty good at being dielectrics. Or it can slowly dissipate into the vacuum via, I don't know, ions or something. It's a charged plastic surface. Eventually, I don't have perfect vacuum, so eventually the charge will bleed off. But that takes weeks. It takes weeks for this thing to stop making thrust. I have bled the vacuum down, pulled the thing out, taken it apart, stuck it in a plastic baggie, put the baggie in with the notes, and come back 3 months later just to see what was going on, and gotten severely shocked from the charge that's still in and on the plastic.
So let me ask you this: if you're able to produce these and they retain the thrust, are you able to stack those up?
Yes. Yeah, they work fine.
And they work fine. So how thin are they?
So why don't I just stack up a couple of hundred of these things in a box and stick it on a scale?
Yeah. Yep. That's what I'm wondering.
You'd be amazed at the result of what that test would be should I decide to run it someday. Yeah.
So what's your loss factor when going from all of them being flat versus all of them being stacked?
Loss factor? Like volume?
Well, you said if it was, 10 square feet, it would be a Newton versus if it was 10 square feet but stacked, meaning it was just...
Okay, thank you. I understand now. Roughly, it's about 10 to 1. I generally speaking, I make about a millinewton per 10 square inches, roughly speaking. Yeah, ish. On a great day. That's all by itself, just hanging out, being happy. When they're in the version that I can zero contact and stack them up, 100 micronewtons is a good day. The first one, it starts out because of the way the charge kind of builds up on the surfaces, because half of the ITO surface ain't got no metal on it, so it tends to pack up a little bit of charge, and then you start getting into some mischief. But roughly speaking, if I had 3 of these things with no ITO around them, with no pockets, no shielding, and they were, sufficiently far apart from each other so they weren't screwing with each other, I would be able to make 3 millinewtons. But when I put them in their little plastic shields and stack everything up and press the button, I can make about 300 micronewtons. about a 10-to-1 loss, which is considerable. Don't get me wrong. And that's not taking into consideration any bound charge. Because if I run these things long enough, I'll
You'll
build
end up
up.
with bound charge,
I'll
and that will
pack
give you
up 3 millinewtons worth of charge on the
a
surfaces.
false. It will
Right.
give you a false negative because the noise floor or the thrust floor just rose. So
Right.
yeah,
So, and that's the problem I have right now is I've run these things. So I do it every day, so this is about 18 times now since Christmas, maybe 20 times, and I've just packed up so much charge on these little plates that
maybe the ITO is your problem because you mentioned that you're only got metal on one side. Maybe
I'm sure it is.
replace that with aluminum foil.
Yeah, but it looks stupid.
Yeah, but make it look stupid and see what it does.
Yeah, I've done it before. It works.
Have you tried mu metal?
No, because there's no magnetics involved.
Okay.
Mu metal is pretty heavy too.
Yeah, this is electrostatic. So the goal here is to do whatever it takes to shut down the electrostatic fields.
Right.
There are no magnetic fields because we don't have any. Again, it's the ITO works fine, and the goal was to show them able to be stacked.
Well, the problem with the ITO that you just mentioned is that there's only metal on one side of it, so you might be creating a thruster that's thrusting in the opposite direction.
Sure, it's possible, and
that's why
that's very possible.
Yeah, so you might want
the surface
to.
Areas, surface areas are the surface areas. They're huge, and I hadn't thought about that.
That might be the reason why. That might be the reason why your numbers are so abysmal for the stacks. Maybe switch to gold. Gold would look pretty sexy, and gold you can make a conductive layer of gold extremely thin.
Yeah, I could also just throw some copper on the other side of the ITO.
That's true too.
Actually,
do that as well.
I found I've never seen it before. They call it thermal shielding. It's PET with a massive amount of aluminum on both sides.
Oh yeah, Mylar.
It might be Mylar, but I think it's PET. But it doesn't matter. Either way,
it's called a radiant barrier. Yeah.
Yes, these. Yeah. Yes.
Is that those are just the little thermal things you wrap around yourself when you're cooking?
Yeah. These are emergency blankets. These are great.
Those have very little aluminum on them. Okay.
Yeah, these are great.
But their resistance is very high. That's up in the mega ohms.
Nah, I'll check it right now.
Yeah, I think you're going to find that the resistance for that stuff is up in the mega ohm range, which is fine. It'd be like an ESD, which would be fine for what I'm even doing. But that and only one side of those things are aluminized. The stuff I found just by pure accident has so much aluminum on both sides, the resistance is down into the ohms. And I've never seen plastic that had so much metal on both sides of it. And I really didn't have
so this is actually measuring them about 1 inch apart. I'm getting 10, 11 ohms. But they are only metallized. It's only metallized on one side.
Yeah, those are only metallized on one side. I didn't realize that they were that low a resistance. That's pretty impressive.
And the probes zero, just straight across each other is 1.5 ohms. So we're talking about 9, 10 ohms because of the resistance in the wire for 1 inch of this stuff.
Well, I guess I could run that. I could run that experiment.
But this has the same problem. This has the same problem that it's metallized only on one side. You're going to end up building a thruster, possibly destructively. You can metalize the other side, or you can pay attention to which side is being metallized and try to use it for constructive.
I did run that test. The problem with putting it's a very nasty mistake to make is putting the metal on the wrong side when you're talking about charging stuff up with 10,000 volts, because the universe will supply mirror charge. So you set up a field, the universe, then that is the ions in the vacuum chamber, because there's no such thing as perfect vacuum. They're going to supply the other side of that plastic with ions. So you set up a field, and let's say you've got a whole bunch of negative over here, and you've got you got the plastic. The universe is going to go and find you, even if this isn't hooked up, this is just
Correction.
plastic. The universe
It's not
can
ions.
find you. Whatever.
It doesn't even need to be ions. It doesn't even need to be atoms. There's electrons everywhere.
Okay, whatever. I'm just saying, those electrons will, if you're negative on one side, the universe is the electrons that are on this plastic, they're going to fly off, and that's what's going to give you the mirror charge. And then what you're going to have is, electrons on one side, a surplus of little buggers, and a surplus of positive holes on the other side, and you're going to read zero net charge. Well, that's all well and good, except when you take away the negative, when you take away this side, then positive holes are still there, and they're there to hurt you. So you can put an enormous amount of charge on a piece of PET. I mean, a stupid, ridiculous amount of charge, enough to shut your heart off kind of charge. That's why these boxes are no joke. We found that out the hard way years ago, and I treat this stuff with extraordinary caution now, because a blast of charge that you just don't even think about it, and you build it up on the wrong side of that plastic, and you touch that plastic for some reason, it will definitely wake you up. I see somebody says that water takes away static charge. Remember, this is all being done in a vacuum. So, water's not your friend in a vacuum. So, anyhow, that's where we are right now. All the effort has been focused on trying to get a structure that can go down to zero so that I can stack these things up and demonstrate stacking. At some point, I'll figure out where all my magic has gone to, and I'll get back to whatever my maximum output is. And then I'll have the best of all worlds. I'll have a stackable solution that puts out, a nice amount of thrust, and then I can just start, I can.
Why is there a requirement? Why is there a requirement for there to be a conductive layer between each thing? Why can't you just stack them as is and put the conductive layer on top? They tend
to kill each other.
They kill each other. So how about a dielectric?
They tend to kill each other.
Even with the dielectric?
Yep. Yeah, I've been down this road for years, Mark. And that ain't no joke. That's why everybody's always talking about AI is going to save us, or whatever. AI ain't going to do squat for science. It can only assimilate data that it already has. We've put our dream into an AI and asked it very specific questions about very specific fields, and it just comes back with gibberish. It literally regurgitates back to us the fact that this doesn't work at all. So the solution to the problem is experimentation, continuous, insane, pointless, repetitious experimentation, where you change one little thing and only one little thing. And if you want to change two things, then you've just wasted that experiment because you have no idea what you've done. So
yeah, that's the tricky part for me. One little thing at a time.
For example, and this is relatively new and impossible to explain, and by positioning our like a single thruster just all by itself in the chamber, inside the ITO box, where it is in the ITO box determines what form of propulsion that thruster is going to make. If it's at one end of the box, snuggled up against one of the ITO walls, for example, it produces electrostatic, differential electrostatic pressure thrust. If it's at the other side of the chamber, snuggled up against the other ITO wall, all of a sudden, the forces that it generates are deviation, or div, the other version of our thrust. Yeah, divergence. Thank you. It's the divergence thrust. And that was exciting because divergence thrust is at a minimum like 1600x what our electrostatic pressure thrust is. And we understand what both of them are, but we've never been able to kick it from one to the other because they're sadly in opposite directions of each other. So all of a sudden, we're screwing around with a known thing, and we're producing known results, and all of a sudden we get a 10x boost in thrust in the other direction. We'll immediately figure out what's going on. So it's like, whoa, let's focus on that because that's way better thrust than the other version, and it costs the same amount in potential, and there's no current in any of this stuff, so it doesn't matter. But turns out I haven't figured out the magic yet in stacking the DIV version of our thrust generator. It's super exciting. I can make a stupid amount of thrust, the characteristics of which are freaking awesome. But I can't stack these things. But when I switch back to the asymmetrical electrostatic pressure, and that's easily stacked. So, these are brand new pieces of information. And our team is working on trying to figure out how we can best, make all this stuff magically delicious.
So, Drew, have you considered or done any experiments where, with a divergence, that you're scaling the pattern of the field?
I do not understand the question.
So, I'm just imagining when you're creating that divergence thrust, you have some kind of pattern that you're putting down to create that thrust, right? Because have a field. And so what I'm saying is, like, take the same pattern, scale it up, scale it down, and see if there's a difference. Because it may be with divergence that what you need to do to get a higher density of pressure or a higher pressure, which equates to force over area, is it's not a stacked thing like with the static, but maybe more pressure per unit area or more force per unit area.
Yes, I have done something along those lines, and that is, I know the field. I know what the field is that I'm running at the test, and when I double the field, I get 4 times the thrust. So it's all about field. So instead of going and just making it twice as large, I do other things to increase the field, mostly jack up the voltage. And as soon as I jack up the voltage, I can make an enormous amount of divergence thrust. But divergence thrust is it's a very tricky thing, because there's a lot of other, we think we actually understand this electrostatic pressure thrust stuff. We're pretty sure we understand it. We have math now, we have simulations of it, we have demonstrations of it. We know what happens when you unplug it, when you let it keep running. We've pretty much just explored the edges of this envelope. But the DIV stuff, that's freaking magic. We have an equation for it, but
The interesting thing is that the divergence is actually what Jim took of the he took the divergence of the field equations to get to derive his effect. So you know, I know it's different with electrostatic, but it's and when you mentioned that divergence thing, it does sound a lot like you know, basically the background pair theory that I talked about last year. And you know, that would be the type of field that would move the background pairs.
Yes.
Yeah.
I do understand, as I understand it, the divergence stuff is a volumetric process versus a surface area process. So, and that's true. By mistake, I increased some volume and magically was rewarded with more thrust. The problem with upping the volume is that it greatly diminishes the field. And when you diminish the field, then you got to jack up the voltage to reestablish the field. So you can make a lot of thrust, but now your toy becomes, you know, you can easily rip your little toy apart because we're already at the edge of the materials. You know? We already
the strength of the material is going to be your limit.
The electrostatic pressure, the electrostatic resistance of the materials, we're so far past it. You know, we regularly have to manufacture new thrusters just because, you know, we just blow holes in them, which is really sad because although I'm good at making these things, it does take some time to manufacture them. But you know, our goal is to find out what the edges of the envelope are and build a spaceship that's powered by these things.
Do you still think that what you're building is a warp drive, or is it just a thruster of some sort?
It's a thruster. I like calling it warp drive because, you know, I can call it anything I want. I invented it. But no, realistically, it's just a thruster. It's a sublight engine. It you know, my understanding of how things accelerate are that you are trading temporal velocity for physical velocity.
That
is the faster you go.
A perfect segue into what I want to show you guys next.
That's because if you're moving faster, you're slowing down in time. Is that right? Yeah, as you're moving faster, you're slowing down in time. Your clocks are moving slower. As you're slowing down, you're moving faster in time. Well, and since the only other way we know of to change time is the warping of space, then I'm going to cheat and say we're warping space. I doubt it. I doubt we're doing that, but I don't know of any other way to explain that we can produce an acceleration in a static device other than the fact that we're changing its time, whatever. I forgot how that all works, but as you're closer to a high mass, you go slower, time goes slower, and as you're further away from a high mass, time goes faster. Well, we're starting out where, you know, the both sides of the stupid thing are sitting still, and all of a sudden they want to move. Well, in some way, shape, or form, we have changed its temporal state. It's the equivalent of in this presence of a large mass of some kind. Well, I know we're not changing the mass of the object because, you know, we're not doing that. It would take trillions of tons of mass to see the same gravitational effect. So obviously, we are doing something that I call warping space. So, anyway, I'm going to humor myself and call it warp drive because there's nobody that's going to tell me not to.
Todd seems to agree with you, but I wasn't able to. Todd DeCiato, warp drive tech. So the link over here, I wasn't able to do a presentation because of my browser software or whatever. But essentially, this is a NOVA presentation and they have a guy out in Colorado who built a clock that is so accurate. He built two of them. It's about 100,000 times more sensitive or more accurate than a cesium atomic clock. It uses frequencies way up there with light. It's extremely sensitive, and they're able to detect differences in gravity between these two clocks when they lift one of them up less than the width of a human hair. So they're lifting one clock up, it's getting farther from Earth, the gravity is dropping. They're able to see a parallax or a change between these two clocks to that degree. So that's a very high level of accuracy. But I'm trying to build a similar device. Actually, Todd was supposed to be working on this project last year. But we're trying to build a project using rubidium clocks, which aren't that great, but they're available. And we have two of them outputting like a 15 megahertz signal going into an oscilloscope. Then we could have one in one location, one in another location. Stick one of them inside of your magic box or whatever's going on, whatever experiment is going on. We'll be able to see if there's a chronological difference between these two devices. So if we can see a change in time, that time is running a little bit slower over here versus what it is over here, that would show up in the waveforms on the oscilloscope. We'd see them shift over one versus the other. That will tell us that there is a warp field, a chronological warp field being created. So I'm curious whether that can be ran with your experiments as well. It'll be something cool to try. Yeah, Todd, your UV laser idea would be a lot more accurate. The thing is also extremely sensitive, and having lasers go through the fiber does cause massive distortions. That's what I predicted when you first told me you were going to do that. And it's way, because every time you shift the fiber optic, it will change the distance that the light needs to go. And the laser diodes, UV laser diodes, they're probably not stable enough for this kind of experiment. Static E fields will distort the rubidium atoms. Yes, they will. That's why they're inside of their own Faraday cage. Put that clock in your static cavity in your styrofoam container. I'm not sure what styrofoam container you're talking about. William, can you elaborate on that? What styrofoam container are you talking about? Curtis, you said something?
Yeah, he may be talking about that. I think you, either you or somebody built a mock-up of what Drew's experiment with using styrofoam. Maybe that's
the early version of Drew's device. Yeah, that could potentially work. Yeah. Oh, another thing we were gonna try is we have these little the little yellow indicators, that the level indicators with a bubble in them. So I got a bunch of those, and we're going to attach them to Campbell thrusters, or basically, stuff similar to Drew's technology, asymmetric capaciting devices, the ones that I had spinning around inside the bell jar over here. And we'll see as they accelerate if the bubble moves. And that will tell us whether there's actual acceleration going on, or this is a warp field being created.
Yeah, I think you might want to start testing the whole divergence thing as well, Mark. Because that's where from the theory side, that's where the action is. And Drew knows this. Oh, you're muted, Drew.
Hate technology.
Oh,
I completely agree with Curtis. Don't get me wrong, this asymmetrical electrostatic pressure, it's cool. But it's the it's the starting point. Okay, we're not going to get to the stars with this. I would be amazed if we made it to the moon with this. But the DIV stuff, that is at a minimum 1,600 times more efficient than our differential electrostatic pressure version, and it's just as easy to make. And I got a pretty good grip on it. So, Mark, maybe you and me, and I don't know, Curtis, if you're bored, we can have a discussion that it's inside of an NDA, because I could show you some stuff that's easily reproducible, and you could be DIV thrusting with your little spinny thing, but with an enormous amount of more thrust. But again, I'm currently working on satisfying some potential customers, customers plural. They have very specific wants and very specific needs, and I just got to the point where, when I saw your invitation for this thing, I was already setting up to run my coating chamber to build the first larger ones, build thrusters that are 120 square inches. So it should be very exciting.
That's exciting. 120 square inches.
It really is. Yeah, really, really is. Considering that my thrusters are, about this big now. I mean, they're you're not much bigger than this piece of paper. And then I'm going to effectively, a 12 by 12 sheet of paper, effectively, area-wise.
Wow,
it's very exciting. But the DIV stuff, that's the answer. Hey, just out of curiosity, is the dude? I don't even know I don't remember his name, but the dude up in like Minnesota or whatever that had the fiberglass and the radio waves. He was going to build a flying spaceship or something, and he does anybody know what I'm talking about? Is that guy still? Is he still in it?
Oh, you're talking about David Perez? He was an old dude.
Yeah, an old dude.
Yeah, and he was talking about the Bermuda Triangle.
Yeah, he had an airplane that went and he got accelerated or something. I don't know what it did. Did he ever? He swore he was on the edge of building a flying airplane thing, hovering thing. Did anything happen with him? Did he go anywhere? Did he do anything? Because I'm convinced that he was on the right track.
He's on the right track. The problem is he doesn't want to work with anyone that he didn't grow up with.
Yeah, that's fine. I can understand that.
Yeah, we've been trying to work with him.
I would really like to work with that guy, but
you don't want to work with that guy. You want to work with his tech. You don't want to work with that guy. Yeah.
I'm just saying.
I tried very hard to work with that guy, David Perez. He'll promise you one thing one day, and then the next day he changes his mind. He has a bad case of inventor syndrome, and he thinks he's going to do everything himself.
Yes.
And in his two-car garage that has one car in it.
That's fine. Anyway, I just we know what we understand the physics of what he was doing, and we're going to launch into that this year.
I know what he's doing too. I understand the physics of it as well.
Yeah,
I have amplifiers here. I actually the guy who builds the linear amps for him is about an hour away from my lab, so we're in contact with him as well. But so the physical hardware of what he's doing, I get my hands on that. The fractal antennas, basically the fiberglass things with the two antennas that go like this. Yeah, that's David Perez. Yeah.
Yeah. We need to all get together on that because we understand the physics of what he's doing. Some of it's nonsense. Some of the stuff he's talking about is nonsense, but we understand the physics of what he's doing.
I believe his technology is probably going to be a lot more powerful than these electrostatic thrusters that you're working on.
Without question, because it's not differential electrostatic pressure that's driving his system. He's actually doing DIV thrusting.
Oh, okay.
He's
That's what
actually
you.
doing divergence thrusting. He just doesn't know it.
No. Yeah,
But
he
that's
thinks it
fine.
has something to do with thunderstorms. He's completely lost on the theory.
Yeah, he
Yes.
thinks he's creating some kind of warp bubble or something. He's not.
He kind of is. Yeah.
No,
I think
really
he is.
not, but
I think he is creating a warp bubble, but
he's not. But that's okay. So yeah, we need to jump on that, because as soon as I speak with my prospective customers, we're going into high gear, really high gear, and that's one of the cooler technologies I've seen over the last couple of years come out of anywhere. He doesn't understand what he's doing, but that's fine.
no,
you know,
and he
I
works.
really
wanted
wanted to work with that guy, but he doesn't want to work with anybody. He wants to.
We tried as
guy.
well. Jared Yates called you up. Before he called you, he was calling David and trying to work with him, and it was the same deal, promising you everything today and tomorrow. It's no, I can't do that. You haven't gone to kindergarten with me. It's that kind of deal.
Yeah. We should discuss that, Drew. I'm in agreement, and I think in terms of the theory and getting more stuff out, I'd be willing to help with that. I think the main thing is experiment, right? If we can show that we're getting something, and then that's there, that kind of gives more information for the theory and picking out, okay, the wheat from the chaff, right? Because with theory, you can only go so far with what we have, right?
Yes.
Experiments that the thing is that we're reaching an area of physics that is unexplored, and so there's going to be stuff that you find in theory that's going to kind of light the way once you think about it and have an understanding of physics and how to think about it. And unfortunately, nowadays, most physicists you're going to talk to are stuck with quantum electrodynamics and quantum itself, and have no understanding of and no training in classical ways of figuring things out. So that's going to be the difficulty you run into.
Yeah,
and so,
fortunately, I don't understand any of that stuff. So the fact that we're violating it or we're proving it means nothing to me, because I don't understand any of it. So I don't think I'm stupid, but when it comes to all that stuff that I don't know. When I listen to Shiva, I have no idea what comes out of his mouth. I mean, I'm sure the guy's brilliant, and I would love for him to explain it to me someday, but I don't get nothing out of it. When you talk about your stuff, I don't understand what you're babbling about, but that's okay, because I'm sure you're right, but it doesn't have any effect. We're still going to have to run the test. We're going to have to run every stupid version of every stupid test until we eliminate the 99.9% of the stuff that don't work. And I'm reading this thing here. Somebody said that it takes 3 GW. Is that gigawatts?
Yeah.
It takes 3 gigawatts per kilogram. What does that mean? I don't know. I make a millinewton of thrust on nanowatts, and I'm telling you, 99.9% of all my energy is
he's
going
talking about
the resistor that keeps me from blowing holes in my plastic.
He's talking of I think he's talking of light thruster. So if you were to shoot EM out one way as a rocket to move 1 kilo in the other direction, you need to have gigawatts going out. That's just rocket conservation of
okay, that's fine. Yeah, we don't do any of that. And that's another thing. I just want to mention this. I got no way to prove it, and of course I'm probably wrong. But the whole, you're violating the laws of conservation of momentum. Well, that would be fine if anybody could actually state unequivocally that they know what the laws of conservation of momentum are. It seems like every day somebody figures out something new about the universe. So, these virtual particle pairs, nobody's adding that stuff up. Nobody's going out there and saying, okay, all right, we have a little box and it's moving 100 mile an hour this way, so we know all the momentum that it has, and all of a sudden you can make it go 120 miles or 100 whatever. You can make it go faster. So you've increased its momentum. Magically, you have to have something go out the other direction. Well, first of all, you have to convince me that you understand what the entire control volume is, because I don't think anybody does. So when you say I'm violating the laws of conservation of momentum, first of all, you better explain to me how you know everything that's in that control volume. Because as far as I'm concerned, the control volume is the edges of the universe. And that's a big ass volume to claim that you know everything that's going on inside of. From, the edge of the known universe down to the whatever Planck scale. You better know everything there is if you're going to claim that I'm violating some law that you know everything there else around it. So that's my, I don't know what the 3 gigawatts for 1 gram is.
I wouldn't, Drew. I wouldn't worry about conservation arguments.
Usually, I don't, because they don't mean anything.
Yeah, and the fact that you're able to get your source of energy with your devices and all of it moves together.
Oh yeah, we're by the way, we made progress on that. We now have I mean, it's no secret. We use commercial power supplies, little mini Spellmans, because they're amazing. But we now have our little mini Spellmans and the little circuit card that drives the Spellman, and the physical switches. We have high voltage switches and all that crap on top of our frame inside of the ITO box. So now the only thing going into the test article section thing is a USB-C cable, and it supplies signal, power, and that's about it. Signal and power, and then the only thing that's coming out of our control volume is a single ground, because we want to make sure that we absolutely have our ITO box true grounded to the rest of the system, not just the ground passing through the USB, because there's possibilities that we might get a little differential between the two grounds. So we have a ground wire coming out, which is a little thin, super, AWG 28 wire, just a little piece of copper. And then we have our USB wire coming out. So all the high voltage is being created inside of our control volume of our ITO box. So we're very excited about that.
That's great.
And, I'm sure we're violating some law of conservation in someone's mind, but we don't care.
Yeah. Well, there's something called with each conservation law has a symmetry of nature, right? That's tied to it, and but there's a caveat to that, and the caveat is that as long as it's not a dissipative system. So what does that mean, right? Well, what that means is that the real world is more complex than the simple law, right? So there could be other things going on, like you mentioned, the vacuum. Like if there's vacuum pairs that you're pushing on, and unless we're measuring directly, we don't know, right? So that's something that saying that something like that is violated is a big deal and needs some proof, right? Now, if you're simply like getting something to move, and we don't have a complete understanding, that's a whole separate thing. And I think what people need to realize is that even though physics seems quite sophisticated, it's not. We do have a good understanding of electromagnetism. We have a law of gravity that makes some sense, but fundamentally, the symmetries of nature that we understand aren't in those laws. So basically, we're basically using a broken physics. Physics is just not complete. It's just we know that it doesn't have we don't have a full thing that's accepted out there. Now there may be people that have that, but that's not the mainstream stuff. So I wouldn't worry too much about that. I would stick with the experiment and doing good work in that regard.
Yeah, that's what I'm planning on doing. So, Mark, how long is this thing? Are we going to run this thing all afternoon, or?
I mean, until we're kind of bored. That was the idea. I actually had some experiments I was setting up over here with this Elzaphone stuff. I got some new wires in. Well, you got anything going on? You got to run?
Yeah, I'm gonna, because I want to get my plates into the chamber, get them pumped down so I can put new surfaces on when I get back from pizza. Because it's pizza night, guys. I don't know what y'all do on Saturday nights. I go get pizza.
Yeah, you go get some of that pizza. That was good pizza.
Yeah.
Try the white slice. That was the best one.
No, I've tried that. It doesn't matter what you do. It's just horrible. No, it needs to be pepperoni pizza. You know, freezing cold soda. That's it. That's what it needs to be. We even have our own warp drive pie. When we go there, I order warp drive pie.
Warp drive pie. Yeah. That sounds good.
Mm-hmm.
So yeah, we should definitely follow up, Drew and Mark, about theory and what you guys are doing. I think in terms of like the last couple of years, what I found that's out there, and what I'm working on, and kind of integrating them. There is a theory system for electrons and for matter that's based on. It goes a lot further than Dirac did. So it's based on you can kind of look at an electron almost as a photon turning in on itself in the theory. That's what they call it. So I'd be really curious, and that group has actually developed software, so you can actually make predictions based on their software of some fundamental things. I'd be really curious what that group of that sector, that electromagnetic sector of what I'm working on. There's the electromagnetic side and the gravity inertial side. Strong forces over there too. But I'd be really curious what it would say about the kind of thing that we're talking about in terms of divergence and that stuff, because my impression is that is, and what I'm working on doing is combining that with the stuff that I've been working on, which is a lot of takes a lot of thinking and takes a lot of time. But I think in terms of the practical matter, the fact that they have software where we can maybe do some computation and try to find out, okay, you know, what could be going on with what you're doing with the divergence. I have some ideas, but I think we really should put some work into that, because the fact that you're getting an effect shows that something's there, and we need to figure out a theoretical mechanism, right, for saying what it is and testing that. And if we confirm that theoretical mechanism, then we may be able to expand what the thrust you're getting is. Curtis, does your whole device run on harmonics and resonance? Yeah, Jim's device, it needs to be in resonance, and it has to be in a positive resonance so that the mechanical waves that are happening correspond with what the piezo stack are doing. I think Old Man Bill has a picture of that Graviflyer, which I found interesting because it had a piezo on top, right? That's the one with the spinning disc.
Yep.
There were a lot of similar elements to what Jim did there, but I don't know, because they're using like these high voltage. Like Jim's not using any high voltage. They're using a high voltage. They have a Tesla coil somewhere along the line. So
we're still debating. We're debating whether that's a scam or not. I mean,
and I wouldn't be surprised if it's like an electromagnetic effect, right? Because if you get a large enough electromagnetic field, you can move things remotely, right? So that wouldn't be surprising if that was going on.
If anyone wants to join the StreamYard, I posted it there in the chat. Nick Carter is asking me why I'm not doing research on intergalactic communication. It's because we're not interested in intergalactic communication.
Mark, do you have any updates on I forgot what it is, whatever it is, where you put the thing in there and you hit it and it loses its mass or it loses its inertia? You know,
Yeah, that's the machine behind me. The
have you made anything? Whatever. Have you got anything to float or not float or?
No, we're not really in the mode of getting things to float. So I'm going to bring the laptop over a little bit to give you a close up on it. So basically, this device was built by a guy named George Hathaway, who really over-engineered the entire thing. But I added my own bit, put the force sensor in there. So the sample is this little guy at the tip, and there's a force gauge over here, and that feeds it over to a computer. So when I touch that, basically throwing the weight over on the computer, you'll be able to, on the computer screen, you'll be able to see it. It basically just swings like crazy. So this is going to go inside the chamber all the way into the magnet, getting hit by RF, and we're supposed to see some magical orientation of subatomic particle spins. And in doing that, it should affect the mass of the sample. We're trying to find a connection between subatomic nuclear spin and mass. So we're saying mass comes from subatomic particle spins, and the wobbles, and by orienting the wobbles, we're able to get rid of that coupling and get rid of the coupling only along the plane and axis of the spin. So we're able to focus mass energy or inertial mass, focus the effects of inertial mass in different directions. So like when we want to move something in a certain direction, we want to get rid of the inertial mass in that direction and move it someplace else. And that's so the amount of mass energy that's stored in the object is actually extremely large, probably enough to boil off all the world's oceans, or at least create a massive bomb. But if all you're doing is not getting rid of it, you're just focusing it, you're just orienting it, that shouldn't take any energy. Or almost no energy. So that's what this machine is attempting to do. Now the latest update, I got some new wires in. This just arrived earlier today. This wire is a LMR 400. It's just long enough. Like I had to actually move my amplifier into this other position in order for it to make it. Just long enough. That's the way you want it. You want the bare minimum of losses. And now that we got this in place, I can try running it at a full 10 amps, 10 watts, I mean. Also, we got this connection in from Israel. It's a waveguide to coax adapter, and I'm going to hook this up to this guy, and I need to connect this also up to the computer. What this will do is will give us the forward and reflected power coming out of the chamber. So we'll be able to see with forward and reflected power, we're able to see how much power the sample is absorbing as we go through a magnetic field sweep, and how much power is coming forward, because these traveling wave tube amplifiers, as they heat up and come to equilibrium, the energy output actually changes a little bit. And those little bits and changes will show up on our reflected power, but we want flat reflected power. We want to see exactly how much energy is coming back from the chamber in relation to how much power went in. So if we put in 10 watts and 5 watts is coming back, then we want to just see the 5 watts. We want to see how many watts are reflected back. And that number, that 5 watts, will change as different resonances are hit. That's called electron paramagnetic resonance, and seeing that over the course of magnetic field sweep. So in the vertical, you'd see the reflected power. In the horizontal, you'll see the magnetic field strength. That's an electron paramagnetic resonance spectra. And using that, you're able to know that you're actually hitting these resonance nodes. And some of the nodes of electron paramagnetic resonance induces dynamic nuclear polarization, which is that subatomic spin orientation that we're trying to achieve.
Well, hurry up.
Nice. So Mark, I have to get going, but I put a link to that theory that I was talking about. That like I said, I contacted that group, but there's a whole rabbit hole for you to go down in terms of like what matter may be. It's really interesting that what it's based on. So, but yeah, I got to get going, guys. You guys have a great rest of your weekend.
Curtis, let's hook up. Let's figure out how we're gonna start working on the DIV stuff.
Yeah, definitely.
So
definitely gotta do that.
This green line over here, you see how it goes straight vertical over there? That's because I touched the sample. And these are just temperature sensors in the room, and they basically show you that the room is heating up because we turned on the heater. It's up over there.
I've got video of actually the latest one is the Blue Origin when they did their hot fire. It takes about 2 minutes for the rumble to make it to my house because I'm about 30 miles north of the Space Center, and I was just running a calibration test, and about 2 minutes after the run, because I'm watching it on my phone because it was really cool watching their first hot fire, and the cool thing was I could actually see the forces show up on the chamber. That's the first time I've ever seen a Blue Origin test. So that was kind of cool. But I've got bunches of tests where I'll be running a warp drive test and I'll be making thrust or whatever I'm doing or coming down off of it. And it's stupid SpaceX rockets. They shake the whole freaking everything, and then they shake my building, and then they shake the foundation, and of course that shows up in the thrust. So I've got all kinds of video of nice smooth test, and all of a sudden SpaceX, and then it just smooths all back.
I got one for you too. Yesterday we had an earthquake. I'm about 3 miles from the epicenter, and it was a 2.4, but it was a very short duration. It lasted about 2 seconds. It felt like a big shock, just up and down.
Really?
Yeah. It was a weak earthquake.
We don't have earthquakes.
Yeah, it was a weak earthquake in terms of total energy, but because the time was so short and distance to the epicenter was so close, it was actually walking distance from my kid's school is the epicenter of that.
That's funny.
What's going on, guys?
What's
Howdy.
up?
Hey,
What are you building?
I was building some Tesla coil stuff, man. Ran into some cool things. I got a video I want to show you guys. Check it out if you don't mind. I'm making Tesla coils ring right next to it and pushing plasma out. I didn't know if it would help in any of you guys' adventures out there.
Yeah, show us your Tesla coil magic.
Well, there's nothing hooked up to it. It's just a number 2 coil sitting next to my regular Tesla coil. But it's what it's doing. It's interesting. So I got it up there. I'll just hit play for you. That's just the number 2 coil sitting next to my regular Tesla coil. You can see plasmas coming both ends.
Okay, so for those of us that don't actually understand what a Tesla coil does, what's going on?
So basically the ring that's coming out of my original Tesla coil, the main Tesla coil, it's picking up in the secondary right there that you just saw, and it's forcing plasma out the end of it. So if you wanted to create some kind of a thrust out of that, and I don't know that you can, but if you did, then it shows you basically the movement of it. So when Curtis was talking about his device and it uses resonance and rings and things like that in order to move motion, this would be the way that you'd want to do it. You'd have to put the ring in there. You'd have to amplify it based on all the frequencies that are in there. You'd also have to put in the harmonic right. And the distances all have to be exactly precise in order for that motion to work. And if you're off on any of it, it'll fail and bounce back on you. So when his readings start going crazy and they bounce back everywhere, it's because his distances aren't perfect. They don't allow for the correct waveform to form inside of there. That's why I show this, because it shows you that there's a lot of power in there that you're not expecting when you run it.
Okay,
That's
so basically that
basically
thing's an
a-
antenna.
Yeah.
Basically, yeah.
Yeah, that's that whole RF power transmission thing. I mean, basically, there's a field all the way around your first one, and you put something in that field that can extract that energy and convert it into some other form, in this case, plasma. So that's kind of cool.
Yeah. So I do something else with this Tesla coil. So, you know, I'll put a rod down the center of it, and I'll flip the field of that Tesla coil and put it into a cold energy form, which basically means it's room temperature and below. And it completely changes the understanding of how it actually works. So it'll go from not being able to touch the energy to being able to touch it all day long and it won't hurt you. But the field that it puts out is a giant radiant field. So you could basically change a lot of things with it. And I can change the electricity from cold to hot and back and forth. And it's making what Tesla would call his radiant field that he was saying was so much more powerful than regular fields. So it's not in this one. I'll show you, if you don't mind, I'll pull up another one for you.
Guys, I got a cut. Hope it all works for you.
Thanks, Drew, for stopping by. Show us what you got, Nathan.
Right on. Okay, give me just a second. So do you know anything about what I'm doing, or?
Yeah, I know exactly what you're. No, I know exactly what you're doing. I saw a presentation at Tesla Tech once where they were using Tesla coils to move energy through the air, which is essentially what you're doing. You're transmitting energy through tuned circuits or tuned secondaries, and they actually used that kind of system to I think it was power like a little choo-choo train or something like that, just as a demonstration. It was a couple of watts of energy. The bottom line is such systems work, and they're extremely inefficient. They are a demonstration of what Nikola Tesla was trying to do in the early days, and they pulled his funding, and that's when all the conspiracy theories came out. But the reality is that people like you, Nathan, probably understand this. This is extremely inefficient way of transferring energy from point A to B. It does work, but it's extremely inefficient.
In that form, absolutely. I won't disagree with you there. It's the flipping that changes it. So give me 1 second. I just want to pull this up for you. Make sure I pull the right one. So what I did with it is I flip it inside out. Sorry. And I put it right to water based on the center of it. And as you can see, it picks up all the energy inside of it in sand and water. Now it's changing the actual field. So what it's doing is it's pushing out all the energy, but I can match it with the actual quartz in there to amplify it. So all that is a bucket of water there with sand in it. And I could put it through other ones like this and to keep transferring the energy through water and everything else.
The energy transfers through space doesn't need to go through sand or anything. Yeah. And you're able to light up those bulbs. Yeah, that makes sense.
Here's the crazier part about it is if I took a 10-foot by 10-foot pond and lit it all up, the energy is interacting with the quartz and the sand. So it gives you the ability to push this much, much further. So when Tesla was doing it in Colorado, he was putting the rod down into the water table itself and interacting with the quartz in the big quarry that he was in. And it was pushing that field so much further so that every time you took like something like this and pushed the light bulb on the ground, it would create light inside that bulb.
Mm-hmm. But just to be clear, we're not looking at an over unity device. This is just a way of moving energy around and lighting up light bulbs, correct?
It's just a different way of moving energy, yes. It's this part's not over unity at all. This is simply how he modified it to create the energy. Now, it would be wrong to say it's over unity because it's in there with the quartz. It's just amplifying the quartz. You know what I mean?
Mm-hmm.
So
how's your Gravenflyer work going?
it's going all right, man. It's all harmonics in that thing. It's all about getting the exact same length of everything to match up, and then knowing which one you're in, first, second, third, or fourth. And when you get to the fifth, it amplifies the energy. I got that thing to put out a tremendous amount of energy. So,
okay. Have you gotten it to tip over or float or any sort of movements?
It doesn't do any of
EMPs?
those things. It picks up energy is what it does. And it creates fields around it. So it basically, how do I say this? If you put in the field normally, it's holding in your static field. It doesn't allow it past the Tesla coil, right? But when you flip and put the Tesla coil on the top and bottom disc, and then the static field to the center plate, it'll allow you to take that Tesla coil and force that static electricity throughout your whole room. So if I'm sitting here, I can take the energy that's going into your computer and I can start making it act like there's a USB device, right? You probably had that a million times. But then it starts to pull up different Google pages based on the frequency that you're putting out of it. You know what I mean? So it's interacting with things in the room and saturating your basically your MOSFETs. So it's basically a field generator.
Mm-hmm. So the videos of Alexei getting it to fly, you think he's doing something different, or is that what do you think's going on there?
I'm not sure what's going on there. There's no plate that I've run across that he could put in the ground that would be good enough to get it to lift. You know what I mean? There's not enough energy there. Even if it is aluminum and you're working with eddy currents to force it up, you can't say that you can debunk them because of that, because you can't create enough force out of it. You would have to have a very large electromagnet to push up 3 pounds of that weight. You know what I mean?
You could have invisible strings, but he does do a lot of, like, with branches. He shows that there's nothing holding it up. I mean,
the fact that he leans over top of it is what gets me. Every time that he does that, you can't see anything under it bending. You know what I mean? You can't see that it's doing anything, but it stays in the same area. So if he's sitting there and there's that much electromagnetism underneath his feet, that guy's catching way too much to be alive. You know what I mean? It's just, that's a lot of magnetism to push that up. So I would think that it's always 50-50 until you can actually replicate it. So I can't say it does work and I can't say it can't. There's not enough to say it can't, but there's not enough to say it does. Even though everything that he said, whether it picks up energy, whether this field works with that field, you know what I mean? Anything like that, when he shows the red light test and the energy going around it, all of it checks out. Just that one last part. Just the one most important part doesn't check out yet.
mm-hmm. And that most important part is the reason why you got into it, right? You want to see it fly.
Absolutely. We all want to see it fly, don't we?
Yeah, we do.
I mean, that's kind of the holy grail. I mean, even if you just look at it as a field generator, it's useful in understanding which fields are holding in which fields so you can know which ones to amplify, right? So if I told you to hold in the static field and you're working on a static field experiment, right? You would like to know that I could put a Tesla coil field around that and then it would hold in that energy, right? So now whatever experiment you're working on, you can now pump up the static. Like I saw you guys doing that tape experiment. And with that, you're dealing with electrostatics, right? And you're trying to get it to hold.
Pinky bed. We're trying to, with the tape that's spinning around. Yeah, we're trying to create a replication of the 3M plant experiment, I guess you could call it, where they saw an effect that rotating electrostatic fields created some sort of barrier. And we're actually feeling some effect there. It's kind of interesting. I need to find a way to up the effect a bit and get stronger electrostatic fields. But that's different, a bit different than the Graviflyer. In the Graviflyer, you have conductors spinning around at high voltage. That's not really rotating electrostatic fields. When you have a dielectric rotating around that has charges embedded on it, and it's rotating around quickly, those static fields are actually rotating around and creating sort of a whirlwind of electrostatic pressure. And electrostatic pressure affects all objects. It's sort of like the magnetism of all matter. So it makes sense that you'd expect certain interesting effects to happen in such a case. One thing that I noticed, though, with that is when we ran the test the first time, we were all kind of scared of the thing because it's pretty ominous, you know. Powered it up, everyone's standing back. We could feel the effects from far away. Then we brought in the meters and we started checking. And the closer we got, the weaker the effect got. And that seemed very strange. Then I had a little THC inspiration, and I realized what was happening is my body, or Tom Butler's body, when he came in with the graph, he's a massive lightning rod. He's shorting out this electrostatic field.
Absolutely.
The closer you get, the more you destroy the thing. It's kind of like in Star Trek or Star Wars, when they're going through the asteroid field and they're getting hit by the asteroids and they're banging off the field, and Scotty comes to Spock and says, oh, the fields are down to 50%, whatever. That's exactly what you're doing. You have these asteroids going into the field, destroying your field. You need to take a step back. You need to get away from it. And once we did that, we started to see the field building up and building up and building up. And then when you throw something into the field, it's actually weakening the field. So that makes sense. Now it can stop it because it has something to couple to. Because you put all this potential energy into a field, it's an invisible field, and you can feel it. If you have hair on your hand, you can feel this stuff, especially with your beard too. You'll feel it. And when you throw something into that field, it actually weakens the field. And that's what's stopping the effect. And with ping pong balls, we were actually able to see, with the field off, it went that far, and with the field on, it didn't make it into the box. We've seen that a couple of times. It's not very strong. I think we need to change out the plastic, and we need to get the thing wider. So there's two upgrades we need to build in this device, but it's looking pretty promising that it's going to work.
Did you take into account the size of the room that it's in order for the amount of static electricity?
Very good point. Yeah, we're kind of at the limit of what that room can handle, because I'd imagine the field is probably, the height of the thing you should probably have at least that distance on either side. So for next tests, we probably want to move it to another room. The problem is one of the contributing factors is high humidity, and New Jersey this time of year is very cold and very dry. So we're really not in the season for invisible walls. Yeah, we need to try this in August when it's invisible wall season.
Yeah, it sounds like it. So you believe that the static alone is the only thing in there that's going to hold the ping pong ball? Is that what the 3M test was originally about? Just static? And
it wasn't the test. The 3M plant they were unrolling polypropylene plastic and making sellotape or whatever they were making with it. And this is a factory that regularly does that. And when they noticed when there was high humidity and high heat, and they forgot to ground the machine out properly, the field built up was strong enough that you couldn't walk through it on the gangway in the device. So that wasn't really an experiment. That was an effect that was observed. And they were trying to get rid of the effect. They didn't want it there. But we're doing the other way around. We're actually trying to replicate the effect and see this effect in real life. And I believe it's there. Right? We're seeing an effect.
Okay. I'm just kind of curious about it. I didn't know anything about it before I watched the experiment that one day, trying to see what you guys were doing. And then Jeremiah came out with the little one. And it was kind of halfway enclosed. And I'm trying to, okay. Was that something that you guys did as well in the same area?
No. So his little one, he's in Milwaukee, and he has his little one. We have our big one over here. This is it right now. It's made out of Connects. It's only about 5 inches width. I would like to make this more like at least a foot wide. Make it a lot wider, because the width is probably one of the contributing factors. Now, if you look at the room from this angle, see what I mean? It's really there's really not that much space on either side of it. So that chair, for instance, that's a field killer right there. Me standing here, this is death for this field. It can't get past me, because I am conductive to these types of voltages and low currents. There's almost zero current in this field. So anything standing there that is even slightly conductive is going to destroy the field.
Well, it doesn't even have to be conductive. It could just be something that clings on to. Any kind of clothing, anything like that, it'll pull right to it.
Yep. It's very easy to destroy this field, which is why it'll work great in outer space, because there's nothing there to attract to. So you'll be able to build it up in space, and then when something comes toward it, you can, stop an asteroid or, manipulate objects at a distance. If we can find a better way to create this sort of field. Obviously, this massive Connects contraption is not a commercial product. This is just this is very much proof of concept sort of theory experimentation level. But very, very proud of it. I was able to hook a 24-volt motor onto the bottom over there, so it's looking really nice.
It looks cool. I'll definitely give you that, man. It looks awesome.
We got 3 different balls for it. So we got bouncy ball, golf ball, and a ping pong ball over here.
You would think the ping pong ball would attract some of that static to it and hold it better, wouldn't it?
Yeah, the ping pong ball does have a stronger effect than the other balls, and it's probably just because of the mass of it. Because I'd imagine a field like this is it's definitely not a warp field. It's more of it's a physical barrier. So lighter objects would get blocked more by this weak barrier than heavier objects. So then if you're playing with it, wouldn't you want to take some kind of styrofoam material that's super light and see if there's movement in the field as you throw it through? Like if it goes in and it swirls a little bit, you learn a little bit more. If it just kind of floats up, you get a little bit more. You know what I'm saying? You understand the flow. So what we're thinking of doing for the next iteration, we're gonna get a bubble making machine, and that would really allow us to visualize it pretty well. Yeah, because if you turn the bubble maker on, with just it rotating around without any electrostatic being applied to the belt, you could account for air currents, and then when you apply the high voltage, you turn the power supply on, then we'll be able to see how that affects it. Bubbles is probably the way to go. That was my brother's suggestion, because those are ultimately lightweight. They don't weigh just slightly more than air. But you want something that's controllable. I want to remove my hand from the equation, because every time I throw something, I'm not throwing it at the same speed, which is why I have this whole the ramp system that we have over here is to remove the human variable. So there's a trigger, and this goes down like that. You see, it triggers downward. Mm-hmm. And what that does is I'm able to release the ball. It goes down the ramp, and then it bounces out, and then that will fall a calibrated distance. If I'm throwing something into the field, I'm only going to see an effect if the effect is really strong.
Right.
I'll only be able to qualitatively tell you that something is happening if it's really strong. If you want a more quantitative and accurate depiction of what's happening, you need to remove the human factor. You need to have a machine, something that will replicate the same thing each time. So a bubble maker, stick a bubble maker over here. It's blowing bubbles into the system. You turn it on, the bubbles make it that far. You turn it off, the bubbles make it that far. That's pretty good. We got some polypropylene over here. This is you can feel it's actually very electrostatically charged. This stuff is it attracts dust. Polypropylene is a common plastic. It's used in, like, when you buy flowers, the plastic on the outside of it, that hard plastic, that's polypropylene. Gift baskets are covered in polypropylene. Lots of food products are covered in polypropylene. It's a pretty common plastic for covering things. So
you replace the tape with that?
We're gonna replace the tape with polypropylene. Yeah. So this is something else that I plan on putting nearby. So this is we had a birthday party the other day and set this up. These are actually conductive, and they are very very attracted to electrostatic fields. I was thinking of taking the streamers down and making some sort of test rig out of that. That would be an interesting way to see exactly what's happening.
So let me ask you, if you wanted to take a static generator and replace the belt on it with each one of these things so you didn't have to use as much material, wouldn't you be able to tell which one's better?
Yeah.
So
yeah, we'd be able to tell. Yes, right now we have Kapton on it. We could take a measurement with Kapton, and then we'll put on a belt of polypropylene. See how that works. So Charlie C, is that Charlie Crawford?
Yes.
Talk to Mike McCulloch about his quantum inertia theory relates to exodus thrusters. Yeah. Drew talked to Mike McCulloch, and he hates him. He doesn't think that he thinks that Mike is trying to take credit for his idea for his experiments. And
so what is he doing now? He was working with what, static electricity before and pressurizing it. Is that what he was doing, Drew?
Yeah, Drew is pretty much making electrostatic thrusters that don't expel any ions or anything like that.
Just the force. That's all he was using?
Yeah, just that. This guy's asking a great question. I would think lower humidity would be better for retaining charge for the effect. Why would higher humidity be better? Would that leak charge into the air too much? Yes, it would leak charge. Maybe leaking charge is part of the effect. This is a good question. We are not sure. But yes, lower humidity would allow the field to build up better. High humidity is basically a leaky dielectric condition of air. So that's a great question.
Interesting.
that's something that we would like to experiment with and try it in dry environments and wet environments and see the difference. The room over there, by the way, is filled with humidifiers and heaters, so we can play around with it. The thing is, in the current weather that we're experiencing here in New Jersey with this extreme cold, very difficult to get that room heated up and humid enough to really like peak it out. We can do dry and cold. That's very easy right now, but the humid and hot is going to have to wait until things warm up a bit.
To be in California, that stuff's easy to make out here. Static electricity, you can fill the whole room with it easily.
Oh, yeah. I mean, right now I could fill the whole room with static electricity too, because it's pretty dry and cold. And I think you guys have the same thing out in California, right? That's why all the fires are happening.
Yeah, unfortunately, yes. That would be us on fire everywhere. So, yeah, I was going to ask you what Drew switches work. So now is he just trying to flip the field?
He's trying to increase the effect, stack the plates. I think that's what's kind of going on.
So he's trying TT Brown's work.
Pretty much, yeah. He's pretty much working on TT Brown stuff and increasing, expanding on it a bit.
I just wondered. I did a test a while back. You can increase the amount of pressure to the plate with static electricity. If you add something in there like paper, because of the mesh format of it, it'll actually produce a higher amount of pressure to the plate because it holds in more of it. So it forces the number of the pressure, you know what I mean, on your plate to give you more. It looks like weight loss, but it's not. It's just pressure. But it would increase it.
Mm-hmm. Well, I think we are getting to the end of what is new here at the lab. Else you got anything to add, Nathan? I think we'll pack it up. It's been over 2 hours already.
Right on, man. Well, it was nice talking to you. I appreciate it.
Nice talking to you. And to everyone out there, live long and prosper. Thanks for tuning in. Have a nice weekend.